Okay, hello everybody. Let's get started. We'll review quiz 3, which was the last quiz you took. And before we go any further, I want to bring to your attention that the pattern that we have established is every other class there's a quiz after the class. So somebody asked me what the pattern was, and this is the pattern. So I'm going to go over these, and if you have questions or something needs further explanation, tell me please. The first question asks for a transfer function model between the force as the input applied to mass 2 and the position of the first mass. So what we need is a model where position of the first mass is in the numerator and the force in Laplace domain in the denominator. So of course the first step is to come up with the differential equation. So the differential equation for this system, in order to write it, the best practice is always to start from the free body diagram, and all the forces applied on each mass, and write Newton's second law for each mass. So if we look at the first mass here, M1, this is I had a question, I believe, on the last class, and the question was, what is really this one, this x1? And I explained that, and it makes sense to repeat that explanation. X1 is 0 when this mass is at static equilibrium. So x1 is not 0 when the mass hits the wall. So it's not the distance between the mass and the wall. It's deviation from equilibrium position. So that's important to know. So that's x1, and mass 2's displacement or deviation from equilibrium is shown with this variable x2. It receives a force F, external force F, and so there is a force that would slow down this mass, but also the direction of the force coming from the spring in the middle and the dashpot in the middle depends on the relative value of position and velocity. So if we make the assumption that x2 is larger than x1, it means that this spring in the middle is going to be stretched, which means the force of spring is going to be this way for each of these two masses, and also force of the dashpot. Now the value of this force is B1, x2 dot minus x1 dot, and the value of this force is K2, x2 minus x1. And there is a force here coming from this spring that would slow this down, and it's going to be equal to K1 x1. So these are all the forces except for if there was any friction, and the figure indicates there is no other friction. If there was a friction, we use, in this course, we use, unless otherwise said, we use a viscous type friction model, which basically says friction force is proportional to speed. So the faster it travels, the larger the friction force would be. So this is the free body diagram. If you write Newton's second law, it would be m1 x1 double dot is equal to, these two are in positive direction, so K2 times x2 minus x1 plus B1 x2 dot minus x1 dot, and K1 x1 is in the opposite direction, so it receives a negative sign. This is for mass 1. For mass 2, similarly, we can write another equation, and that equation is m2 x2 double dot is equal to, now the direction of these two forces, even though they're exactly the same force, the same two forces applied on mass 1 is in negative direction. So here it will receive minus K2 x2 minus x1 minus b1 x2 dot minus x1 dot. And the last force is this externally applied force, which is in the positive direction. So we have the two differential equations. What is the next step? What is the ultimate goal? Let me ask the gentleman sitting in the very last row. What is the ultimate goal? What are we after?
Trying to find the frequency at which it goes back and forth.
We are talking about the first question. So if you read the first question, please, either from the board or from your notes, we are trying to find a transfer function between force F and displacement x1. So we want a model between these two. So as we move the force, as we apply the force, and it could grow in magnitude or not grow in magnitude, it could be a constant force, it could reduce in magnitude, it could be anything. We want to know how x1, the displacement of mass 1, would respond. That's the question. So what is the next step? Yes?
Rearrange it in your standard form.
We could do that in order to get to the standard form of the differential equation. Or we could simply, and then after that, take it into Laplace domain, or we can take it to Laplace domain right as it is. Either way. So let's try the second approach here. If you take this, let's rearrange. I like that because it will reduce the algebra, will make it easier on us. So if you rearrange this equation, you will get m1 x1 double dot plus b1 x1 dot plus k1 plus k2 times x1 equals b1 x2 dot plus k2 x2. The same thing for the second mass. We'll get m2 x2 double dot plus b1 x2 dot plus k2 x2 is equal to k2 x1 plus so it's going to be, to keep the same order, it's going to be b1 x1 dot plus k2 x1 plus the externally applied force F. Did we make any sign mistakes or anything in the rearrangement? Please let me know. And we'll make a correction. So we did the rearrangement. What is the next step? Again, the ultimate goal is to find the model between force F and x1. And if you look closely at these two differential equations, the first differential equation is between x1 and its derivative and x2 and the first derivative. And if you look at the second equation, we have x2 and its time derivatives on one side and x1 and f on the other side. So we have a mixture here. So if you look at the first equation and take it into Laplace domain, what you will get is m1 s squared plus b1 s plus k1 plus k2. This whole thing will be multiplied by x1 of s, that is equal to b1s plus k2 the whole thing is multiplied by x2 of s. So this bracket closes here. And so that's the first differential equation transformed into Laplace domain. The second differential equation, if you transform it, it will become m2s squared plus b1s plus k2 from one side multiplied by x2 of s equals b1s plus k2 x1 of s plus f of s. So now you have two algebraic equations. So if there is no differentiation anymore, it has replaced with powers of s. Whenever we had dot, it has been replaced by now by powers of s. Now these are two algebraic equations. So the next step is to simplify. Between the two of them, what are we trying to get rid of? What is the unwanted variable between these two equations? We want our transfer function to be what over what? What is the output? We are looking for x1s as output and f of s as input. So we want x1 of s up here and f of s here as the denominator. So neither of these two equations can give us that relationship. So you have to eliminate, there are three variables involved here, x1, x2, and f. So you need to eliminate x2 in order to find that relationship between x1 and s. So that means from the top equation, you need to find x2. So from the top equation, x2 of s will be equal to x2 of s will be equal to m1 s squared plus b1s plus k1 plus k2 over b1s plus k2 times x1 of s. Can you see that? So x2 is that in terms of x1. So what is the very last step, or one step before last, is to substitute for x2 in the second Laplace equation. So whenever we see x2, we are going to substitute that. And as soon as you do that, you will no longer have x2 available. So now we are looking at this second equation. So I'm going to rewrite that second equation. So m2s squared plus b1s plus k2. Now that we have x2 of s, I'm going to replace it with this ratio that we just found. So it's going to be m1s squared plus b1s plus k1 plus k2 in the numerator. And in the denominator, we have b1s plus k2. And this is multiplied by x1 of s. So that's this portion. And this is equal to make it a little bit easier, please follow me so there is no confusion. So I'm going to take this term from the right side and move it to the left side. So we have every term that has x1s in it on one side. So I'm going to take this term and bring it here. So it is going to be minus b1s plus k2 also times x1 of s, and this is equal to f of s. So we have now one equation that is only between the two variables of interest, x1 of s and f of s. So the next step is to form that ratio. Now, in order to add these two items from the left side, I need to make b1s plus k2 the common denominator. So in order for them to become 1, that needs to be the common denominator. So if you make that the common denominator, so if you bring this here, which is b1s plus k2, this simply goes to power 2. So the equation remains unchanged. So if you bring that denominator to the second part of the left side of the equation, you need to take the numerator to power 2, so you wouldn't change anything. Now we are ready to form that ratio. So x1s as the output over f of s as input is going to be equal to, so what goes in the numerator? The common denominator will become the numerator for the whole thing, so it becomes B1S plus K2. Can everybody see that? That's what is being multiplied by f of s, so that's why it needs to go to the numerator. In the denominator, we will have what? We'll have the multiplication of these two terms. So we have, let me start by a bracket. So we have m2s squared plus b1s plus k2. This will be multiplied by m1s squared plus b1s plus k1 plus k2 plus k2, and from it we have the subtraction of b1s plus k2 plus k2 to power 2. This line. So that's the transfer function. What is the order of the transfer function? What is the order of this system? It's fourth order, because the highest power, if you carry out this multiplication, you don't have to. If you carry out this multiplication, you would see s to power 4 is the highest power in the denominator, therefore it's a fourth order system. Was this the question? Was it the end of the first question? So it says find the transfer function model between the force and the position of the first mass. So that's what we got. And then the next one asks for a state space model between the force and position of the first mass. Essentially, it wants the exact same model now in the form of a state space. Now, before writing the state space model, so we are now talking about the second part, what do we need to identify? We need to identify the input, the output, and the state vector. So let's start by input. What is the input to the system? So I'm going to write U and wait for you to tell me what the input is going to be. Input, anybody? We said it in the definition of the problem. The input is force. How about the output? Remember, in many of the problems in the past, we said we have a choice to make for the output. Do we have a choice to make here for the output, or it's clear? It's clear. We are looking for a model between force as the input and what as output? Position of the first mass. Now, because we are going to use x, it's distinct enough because it's x1. So x1 is going to be our output. So we need to decide about the x vector. So what is going to be included in the state vector? What are the state variable? So these should be there. So x1 and x1 dot. Anything else? What is the order of this system? We already know the order of this system is 4. And a fourth order system has how many state variables? It has 4. So what are the other 2 state variables? They're x2 and x2 dot. And always a state vector is a column vector. So if you write it as a row vector, you need to put a transpose sign so you know it's a column vector. Okay, so we got this. The next step is to form the state space model. So x dot means x1 dot x1 double dot x2 dot and x2 double dot. That's the meaning of vector x dot. And in the state space form, we're trying to write it as a matrix A multiplied by x. So matrix A, which we don't know what it is, we are going to find it. This gets multiplied by x, which is this. X is, as we just defined, x1 dot, x2, and x2 dot, plus b, which we haven't found, b multiplied by u, which in this case is force F. So it's another way of writing everything out so it's clear what x is, what u is, and what we are looking for. Okay, so row 1 of matrix A simply says, what is x dot in terms of these members of x? So I'm waiting for you to tell me. What is x dot in terms of these 4?
0, 1, 0, 0.
It's equal to one of them. And in order to communicate that, you're saying, in order for that to happen, x1 dot is 0 times x1 plus 1 times x1 dot plus 0 times x2 plus 0 times x2 dot. That's what we are saying by putting 0, 1, 0, 0, and well, we are added another 0 times f. So x1 dot is equal to this expression. So any doubts why we are doing this? So basically we are saying, let me repeat, we are saying this is equal to 0 times x1, 1 times x1 dot, 0 times x2, 0 times x2 dot, added all together. That's the meaning of matrix multiplication. You multiply element by element and then you add the results. That's the rule for matrix multiplication. So that's what we are telling. The story that line tells is that. Okay, so let's look at x1 double dot. x1 double dot, if you look here, x1 double dot, we have an expression for it. It's right here at the bottom of this slide. This equation, if we call it equation 1. So equation 1 has the expression for x1 double dot. So what is x1 double dot equal to? It is equal to, you need to divide the whole thing by m1 to single x1 double dot out. So you need to divide, once you divide that, you would see that what is multiplied by x1 in that equation, which is the first member of state vector. So what is multiplied by x1? It's minus k2 rather, isn't it? It's k2 divided by m1. Is this k2? Can you see that?
So in the first equation?
In the first equation, yeah, right here.
There's also a k1 of x1.
Absolutely, you're right. So there's a k2 and there's a k1, so we need to add them up. So both have negative sign. So therefore, what gets multiplied here is minus k1 plus k2 over m1. So minus belongs to the whole thing. So that's what is multiplied by x1. Going back to the equation, the next element in the x vector is x1 dot. What is multiplied by x1 dot? It's negative b1 over m1. So we go back here and write negative b1 over m1. Again, go back up. What is multiplied by x2 in that equation? Seems like it's only k2 that is multiplied by x2, so it's going to be k2 divided by m1. So the third element is going to be k2 divided by m1. And the last element is what is multiplied by x2 dot, and it seems to be b1 with a positive sign. So it's going to be b1 again divided by M1. So B1 divided by M1. So we got the 4 elements of the second row. So the second row of matrix A is now clear. Okay, let's go to the third row. And I really need your help in finding those. Okay, by the way, in this equation, in equation 1, was there any F trace that you can see? So that means what? That means the second row of F is also equal to 0. So there is no F involved. Okay, so let's go to the third row now that we have row 1 and 2 of both matrix A as well as matrix B. So what is the third row? The third row on the left side is what? What do you see as the third row of matrix X, vector X dot? You see, what is it? X2 dot. Now X2 dot is, how is it a function of these 4? X2 dot is equal to the fourth one. So basically what you're saying is X2 dot is equal to 0 times X1 plus 0 times X1 dot plus 0 times X2 plus 1 times X2 dot plus 0 times F. That's what you're saying. So you can basically put a 0 here, a 0 here, another 0 here, a 1 here, and of course a 0 here. There is no 0. There is no F otherwise in that equation. So we got the third row. Did we put the 1 and 0s at the right place? Okay. Now the last equation basically is the equation for X2 double dot, which we can get from this equation, the equation 2. So X2 double dot is a function of X1, X2, X1 dot, X2 dot, and F for the first time. Okay, so what is multiplied by X1? Let's start there. What is multiplied by X1 in that equation? It's plus K2 divided by M2. So plus, so let's go here. So K2 divided by M2. So we got what is multiplied by X1. Let's go and find what is multiplied by X1 dot. What is it? In equation 2, what is multiplied by X1 dot? B1 divided by M2. So positive B1 divided by M2. What is multiplied by X1 dot? Oh, I'm sorry. The third element is X2. So what is multiplied by X2 in the second equation? It's negative K2 divided by M2. So negative K2 divided by M2. And the fourth element is what is multiplied by X2 dot, which is negative B1 divided by M2. So negative B1 divided by M2. And there is a 1 here divided also by M2. Because that's what's multiplied by F. So we found 2 matrices, and no surprise, matrix A is 4 by 4. This is a fourth order system. And matrix B, it's 4 by 1. 4 because it's fourth order, and 1 because there is 1 input. So 4 by 1 is our matrix B. Okay, and we know our output is Y. Y as output is equal to what? Which one of these 4 state variables? It's equal to? We decided that our output is going to be equal to, which means the row matrix, or row vector rather, is 1, 0, 0, 0 times x. This is our C matrix plus 0 times U. So we found A, B, C, and D, the 4 matrices that together make the state space model for this system. So we're good so far? So now let's go to the next question. Find the transfer function model for the system, this electric system, and between voltage and electric charge. So we want a transfer function and followed by the state space model between voltage and electric charge. So what we need is the equation. So let me go ahead and add a page. So Kirchhoff's voltage law basically says, in terms of current, we have Ri plus L di over dt plus 1 over c integral of I dt, and that's equal to the applied voltage V. That's the basic Kirchhoff's equation. And what is charge? What is the relationship between charge and current? It's integral of current, I dt, which means Q dot is equal to what? And Q double dot is equal to? Yes, very good. So we are going to use this notation and write this as L Q double dot plus R Q dot plus 1 over CQ, and that is equal to V. Now, in order to find the transfer function between Q and V, we need to do what? We need to take this equation into Laplace domain, which will give you L s to power 2 plus R times S plus 1 over C, which together gets multiplied by Q of S, and that is equal to V of S. So immediately you have the model. So the model between Q as output over voltage as input is equal to 1 over Ls squared plus Rs plus 1 over C. And what is the order of this model? Second order. Let's move on to the state space model. So we need to identify the input. What is the input to the system? The voltage. What is the output? Is Q. And what are the state variables? For that, I'm going to wait on you. What are the state variables? And we know there has to be two of them. It's a second order system. State variables, everybody? It has to be Q and Q dot. So Q, Q dot, that's it, column vector. Okay, now let's find that. So X dot is going to be a 2 by 2 matrix times X plus a 2 by 1 matrix times input. Okay, what is row 1 of matrix A? It has to be 0, 1. So basically we are saying the first member of X dot, which is Q dot, is equal to the second member of X, and there is no voltage in that equation. So Q dot is equal to Q dot. Now what is Q double dot, which is the second member of X dot, equal to? If you look here, we didn't write it in that form, but if you take the Q dot term and the Q term to the other side, you can see Q double dot is a function of Q dot, Q, and V, which is the input. So what is multiplied by Q, which is X1? Remember, it has to be on the other side. So it's not 1 over C, it's negative 1 over C, and it has to also be divided by L. So it is going to be negative 1 over LC. That's what is multiplied by Q1. I'm sorry, Q, which is X1. What is multiplied by X dot is minus R over L, and what is multiplied by the voltage is 1 over L. And for the C matrix, we simply have 1, 0 plus 0 times 0. So that's I believe this is the fourth question. Let me make sure. This fourth question was find a state space model for the system, again, between voltage and electric charge. So we found that. And okay, so that was the fourth question. Any questions so far? So the next question was on a transfer function model for the pendulum. It's specified the input as a torque applied. It also specified that there was friction, and we are looking for a model between the applied torque and the output angular position. So that means the transfer function that we are looking for, g of s, is between theta of s and t of s, where t of s is the applied torque. That's what we are after as the end result. And if you remember, the basic equation was Newton's second law in angular form or in rotary form, and that essentially says J theta double dot is equal to all the moments, and the first one is minus B theta dot. The second one is the applied moment or applied torque that causes the motion, and the last one is from, let's draw the free body diagram. So free body diagram, this is massless, this has mass L. There are two reactions here. There is an applied torque T, and there is an opposing B theta dot torque. And here the force is mg. So if you're adding all the moments about this point, call it point O, for example. I can write O anywhere. So if you're adding all the moments about point O, we already talked about T, which is applied by a motor. We also talked about B theta dot, which is the moment applied by the friction slowing down the motion. What is left? Is there any other moment that I need to include about point O? Yes?
Negative L sine theta mg.
So there is a force mg pulling this and causing a clockwise rotation, which is negative. By the way, theta is measured this way. So this is theta measured from this point on. So there would be a negative moment of mg is the amount of force, and L sine theta is the moment arm. So that's the equation. And we know J is mL squared. So we have mL squared theta double dot plus B theta dot plus mgl sine theta, that is equal to T. Now this is a nonlinear differential equation. And we said it, we are not able to transform this into Laplace domain because the fact that it's a nonlinear differential equation. So what do? We find a linearized version of it. So we found two linearized versions of it. One linearized version about theta equals to 0. The other one about theta equals pi. But you can linearize it about any point you want. But these are the most convenient points, and because there are equilibrium points of the system, they make sense to be. So we are going to linearize this around theta equals 0. So if theta remains small, so theta remains small means this pendulum stays close to theta equals 0. The linearized version of this equation comes from the fact that around that angle, sine theta is approximately equal to theta if theta is expressed in radians. That's another thing to remember. So if the unit of theta is radians, sine theta and theta are almost equal if we stay close to theta equals 0. So we can take advantage of this approximation and write our differential equation as mL squared theta double dot plus b theta dot plus mgl, this time theta instead of sine theta, equal to capital T. Now we are ready. Now we are ready to take this and into Laplace domain. If you take this into Laplace domain, we'll have m L to power 2 s squared plus b times s plus mgl. This entire is multiplied by theta s is equal to T of S. Now you're ready to form the ratio. Yes, sir.
That first equation where you turn j into ml squared,
Mm-hmm.
should it be 1/2 ml squared?
Is it 1/2 ml squared from the previous solution?
Yeah, the last example we did a while back was 1/2.
So let's stay consistent. I think you're right. I forgot, and thank you for reminding. So it's ml squared over 2. Thank you. And also here on the very top here. Thanks. So ml squared over 2 is that's the J value for a concentrated mass where the link has no mass. So that's the equation. Okay, so we are ready to form the equation for the transfer function. So theta of s as the output over t of s as the input is going to be, so we have a ratio where 1 is here, and in the denominator I'll have ml squared s squared divided by 2 plus b times s plus mgl. So that's the transfer function. And what was the last equation for the quiz? The last question rather is a transfer function this time between applied torque and not angular position but angular velocity. So it's asking for a new transfer function not between t and theta but between t and omega, which is the angular velocity. Okay, so the approach there is to recognize that omega in time domain is equal to theta dot, which is derivative of angular position theta. Now if you take this, just this, into Laplace domain, capital omega of s is going to be equal to what? What is the Laplace transform of theta dot? S times what? S times? So there is an S because of the first time derivative. Times what? Times. So let me remind you. So if we have f of t, Laplace transform of f of t is f of s, like that. If you're looking for Laplace transform of f dot of t, if all initial conditions are equal to 0, it's going to be f of s times s. So that's the basic equation. Again, if all initial conditions are equal to 0, which is our assumption whenever we are after a transfer function. Okay, based on that, what goes after s in my omega equation? What goes after s? See, my f of t is theta.
So we want to keep it in terms of theta.
We have no choice. If Laplace transform of f of t is f of s, Laplace transform of f dot is going to be s times f of s. Now, Laplace transform of theta, because we don't know what theta is simply theta of s. So this equation, therefore, is s times theta of s, which we have done it many times. So when we took any differential equation into Laplace domain, including this very last one, didn't we do exactly that? So when we had theta dot, we replaced it with b basically S times theta S. That's exactly what we did. So when we have theta double dot, we replace it with S squared theta S. When we have theta dot, we replace it by S times theta. And when we have theta, we simply transforms as theta. Okay? So that's the basic equation. Now that we know this, we know we are after this transfer function. We are after a transfer function between omega as the output and t as input. So that's the question. Now, what I want to tell you is that you already know the answer. You already have the answer. You have a transfer function between t and theta. You have a relationship between theta and omega. So can you bring these two together in order to find this transfer function? Too early to ask this question or this kinds of questions? But think about it, 30 seconds. You are after omega over t. You already know what theta over t is going to be. Yes. So it is, you're absolutely right. So you're basically saying, let me rewrite what you just said. You said this is omega s over theta s multiplied by theta s over t of s. So if you multiply these two ratios, don't you arrive at omega over t? Theta and theta will cancel each other. Now, do we know what omega over theta is going to be? If you look here, do you know what omega over theta is going to be? What is it? It's s. So write an s here. Do you know what theta over t is? Where do you have that information? Up here. So take this and multiply it by 1 over m L squared S squared over 2 plus BS plus MGL. So you got it. And that's a common trick. When you have a transfer function of a base variable to an input, and you're looking for the transfer function of time derivative of that variable, you simply take that transfer function and multiply it by s to get the new transfer function. Any other questions about the quiz? Okay. So last time we introduced two laws, the law of motors and law of generators, that brought the mechanical domain and electrical domain together. It was the basic, there were these two basic laws that brought these two systems together. Law of motors basically tells you how much force is generated. If you have a wire in a magnetic field and that wire carries a current I, if that is the case, there would be a force generated. And the counterpart law, which is law of generators, told you if you have a wire that is, again, in a magnetic field, but this time the wire actually moves. So we move the wire. If that happens, then you generate a voltage, and that voltage is proportional to the magnetic field strength, to the length of the wire, and to the speed of travel. That's called law of generators. And we brought these two laws into finding an equation, or actually more than one equation, for this system. This was a DC motor. We mentioned it has an electric part where you have a source of voltage and a winding of wire. That winding of wire definitely has a resistance. If we had a wire with no resistance, we would be very lucky. There would be no loss. But any wire you have would have resistance. So R represents that resistance. And it also has an inductance. L is that inductance. And we said as soon as you apply a voltage, a current would develop. And because of the existence of the current and the wire in the magnetic field, you start creating a force. And that force is applied to that rotor, and a rotation starts happening. Now, as soon as you start rotating that, because now you have a wire that is moving in a magnetic field, you will start generating some voltage according to the law of generators. Unfortunately, that voltage is going to oppose the main voltage. We call it back EMF. And we found the back EMF up here. So it was proportional to speed of rotation of the rotor. And based on that, then we wrote this equation for the electric side. And in that equation for the electric side, you have now theta dot, which is the angular velocity. So you connect through the electric side to the mechanical side through angular velocity. And when you write the mechanical equation, which is Newton's second law for this rotary system, you have j theta double dot plus b theta dot, which the second term representing all the friction. Then you have the law of motors, basically showing how much force or how much torque in this case will be generated according to law of motors. We took the two differential equations, which is the one coming from Newton's second law, and the second equation that comes from Kirchhoff's law, and took it and wrote it in the form of a state space model. Did we also do the transfer function? Yes, we did. We took both of these two models into Laplace domain and formed a transfer function between the applied voltage and the angular position. And where we left was on this at the top of this slide. I ask you, find a transfer function between applied voltage and angular velocity. Don't you already know the answer by now? So I'll give you a few seconds. Write the answer. What is, so you already know the transfer function. You know the transfer function between voltage and angular position of the DC motor. And based on the denominator of the transfer function, you can see that it's a third order system. There are three state variables, theta, theta dot, and the current. So we already have a transfer function between voltage and angular position of the motor. Can you find now a transfer function between voltage and angular velocity? So what is the answer? Anybody? That's the answer. You just multiply the top by s. Why? Because omega and theta dot are related, as you see on the top. So omega is first time derivative of theta, which means essentially that capital omega s is equal to s times theta of s. As soon as you have that relationship, then you can find the relationship of omega and v of s. So if we call this g of s, omega over s is going to be equal to s times g of s. So by multiplying the base transfer function by s, you find now a model between applied voltage and output angular velocity. Now, if you were to make that change into the state space model, what would you do? Which portion of the state space model you have to change so you have a model between the applied voltage and output angular velocity? Let me bring up the model that we already found. This is the model that we already found. So which part of this model will you change? So the output of the system would be angular velocity as opposed to angular position. Which part? Remember, the state space model has 4 parts, A, B, C, and D. Which one will you change? Absolutely. There's very minimal work to do. Very much similar to minimal work that was involved in the transfer function. The minimal work involved is just to change matrix C. Remember, the dynamics of the system, which is reflected in the first part of the state space model, will not change based on your choice of output. That will remain the same. So A and B will not change based on our decision of what will be the output of the system. It's only a matrix C that would change. Okay, so if you are ready, we are going to look at another system, which is another electromechanical system. This system is a speaker, essentially. So we use speakers to create sound and to have it an amplified level of sound. So what is not shown here is a microphone and an amplifier. So you have a microphone that captures the sound waves, the pressure waves, and turn them into an electric signal in the form of a time-varying voltage. And that time-varying voltage gets amplified and then comes into this circuit. So this circuit receives a voltage that is amplified version of the signal that the microphone records. Now this, in turn, derives an electric circuit. And this electric circuit has also another wire winding, and it interacts with a magnet. Now, in the interaction with the magnet, what it creates based on the level of this voltage or variation of this voltage is mechanical motion. And that mechanical motion is the amplified version of the sound. So this mechanical motion, this vibration essentially, creates the sound in with a higher intensity. So if you look here, there is this cone which represents the shape that directs the sound. This is the cross-section of the collection of wires that move in the magnetic field. And so that's the physical system. And this cone is basically suspended in a frame to give it basically less potential for interaction between frequencies. So this is the magnet and the coil. This is the schematic of the entire speaker. Now, this says low force suspension means that this connection acts like a damper, but no spring. So the function that we want is quick attenuation of this vibration. So when we create one frequency, we don't want this frequency to linger around for the next frequency to arrive. So we don't want mixing frequencies. So we want a high damping membrane that creates the cone section of this speaker. So essentially, that's what an ideal speaker looks like. Now on the electric side, let me again talk about the electric side. We have the source of voltage, that is the amplified signal coming from the microphone. The coil has a resistance and the coil has an inductance. And because the coil moves in a magnetic field, we are going to unfortunately create another back EMF here. So we are going to generate a voltage that would be opposing the voltage, the amplified voltage that derives or drives rather the whole circuit here. So again, the objective is to first of all come up with the differential equations, and then we can take it into a state space form, a transfer function form, and so on and so forth. So if you look at the mechanics of it, because this coil or the moving parts have a mass, if you write Newton's second law, you have mx squared equal to all of the forces. So mx double dot rather is equal to sum of all the forces in x direction. And one of them is the force that is generated according to the law of motors. So you have a wire in a magnetic field and you pass current through it. So according to law of motors, the force generated on that coil is B, magnetic field strength, times L, length of the wire, times the current, which is a time variable. So it's BLI. And what slows down this mechanical motion is the damping that is caused by this mechanical structure. So it would be BLI minus Bx dot. And you can immediately see that even though it's a mechanical equation, the trace of electricity or the electric side of the system is in there. So the current appears into this equation. So if you rewrite this equation, you have mx double dot plus bx dot, which goes to the other side, is equal to B, capital BLI. So this basically tells you how much or what is the level of vibration. X determines the displacement of that diaphragm. So that was the equation, the second order differential equation we get from Newton's second law. If you look at this circuit, Kirchhoff's law, you have a source of voltage, you have resistance, you have inductance, and you have the back EMF that, as I explained, is created because your coil moves in a magnetic field at velocity V. So Li di over dt is the voltage drop here. Ri is voltage drop of the resistor. Va is the deriving voltage that comes from our amplifier. And E is the back EMF, which acts like a voltage drop. That's why it belongs to the voltage, to the same side when we are adding voltage drops. Now, the voltage drop, according to law of generators, is equal to strength of the field, length of the conductor, the wire, times velocity of travel. Law of generators basically says the faster you travel, the more voltage you create. So this is going to be BLX dot. So we have two equations, two differential equations. One of them is second order, one of them is first order. Second order because we have x double dot, first order because we have di over dt. So this system, therefore, like the electric motor, is a third order system. It's a third order system. So what are the state variables here? So state variables, I'm going to use an underline so it's not mixed up with the position and velocity. So state variables are position, velocity, and current, like the case in DC mode. So these are the three state variables. Input is the voltage, again, that comes from the amplification of the signal from the microphone. And output generally is the position. We are interested in the vibration that is created, and that is going to be x as a function of time. So your first assignment, I'll give you a couple of minutes, is to find a transfer function. Find a transfer function between armature voltage, VA, and the displacement, x. So find a transfer function. Okay, so let's work together now that you had some time to think about this problem. So by now we all agree that the first step is to transform these differential equations into Laplace domain. So if you knowing that all initial conditions are going to be equal to 0, so if you transform the the first equation, you get m, it's a constant, multiplied by s squared plus b multiplied by s. This whole side gets multiplied by x of s. So there's an x of s that comes from each of these two. I'm just combining them so it's quicker to see that x of s is involved in both of them. And on the right hand side, b is a constant, or that at least that's our assumption. L is a constant, but I is a time function. So I'm going to transform this to Laplace domain as I of s. So BL times I of s. So that's the first equation. We'll do the same thing for the second equation, where we are going to get L times S plus R times I of S. That's the first two portion. E of coil, I'm going to add it here as BLX dot. How does this transform to Laplace? So let me go ahead and put the sign here, plus. So we have BL times X dot. How do you transform this to Laplace? It would be B, which is a constant, times L times S x of S, which is Laplace transform of X dot, and that is equal to VA of S, which is also a time function, but we don't know what time function, so we're going to keep it general. And so we have two equations. Now both algebraic equations, there is no differentiation anymore. Please keep that in mind. If you do your Laplace transform and you still have dot or double dot, you've made a mistake. So go back and redo the Laplace transform. So there is no time anymore, there is no differentiation anymore when you are done with your Laplace transformation. Okay, so we need a ratio between x and v. In other words, what do we not want in the mix? What variable should go away? I of s should go away, which means you have to find I of s from the first equation and then incorporate it into the second equation to get rid of it. So according to this first equation, I of s is ms squared plus bs times x of s divided by bl. So I'm going to rewrite the second equation with that in mind. So the first portion will just repeat, ls plus r repeats. When we get to I of s, I'm going to write it as ms squared plus bs divided by capital B times L. And this entire expression is multiplied by x of s. And we're going to move to the second part and write B times L times x of s. That is equal to VA of s. Now we have one equation that is between the two variables of interest. So there's just a bit of more algebra to do, and we are going to be there. So what is the next step? We need to make BL our common denominator so we can combine these two terms. So if you make BL your common denominator, this becomes B squared L squared. And then we can now go ahead and write a ratio. So we are looking for a ratio of x of s in the numerator over VA of s in the denominator. So B times L goes into the numerator of the resulting ratio. In the denominator, we'll have LS plus R. Let me go ahead and multiply the whole thing so it's easier to see that this is a third order polynomial. So if we carry out the multiplication, we are going to have m times L s cubed so mls cubed plus two terms that would be s squared. One is um, L times B plus R times M times S squared plus, there are two terms that are S to power 1. One is R times B, and the second term is B squared L squared. Is it clear that we are dealing with the third order system now? Okay. So if I ask you, find a transfer function between applied voltage and velocity of motion of this diaphragm, should be able to quickly answer that simply by knowing that x and v as position and velocity are related through a multiplication of s. Therefore, relationship between velocity and applied voltage simply would be so if this is g of s as we indicated at the top, so velocity over VA of S is going to be S times G of S. Okay, so your next assignment for the next minute is to find now the state space model for this system. Please go ahead and find the state space model for this system. The equations are here. So we need to find a state space model. So in the first part of the state space model, we are answering this question: how x dot is a function of x and u. This is a third order system, so this is going to be a 3 by 3 matrix. And this is going to be a 3 by 1 vector. Okay, so row 1 of that equation, we already decided that x is going to be made of position, velocity, and current. So the first member of x is position, therefore the first member of x dot is velocity. So how is velocity a function of members of x? So in other words, what should go up here? The answer is 0, 1, 0. To simply tell the story that velocity is equal to velocity. So the second line basically tells the derivative of x dot is x double dot. So how x double dot is a function of the rest. And the answer to that question, how x double dot is a function of the rest of the state variables, come from this equation. This equation says x double dot is equal to, if you take b x dot to the other side, is equal to minus b over m x dot minus b l I over m. So basically this tells you, this says x double dot is equal to minus b over m x dot minus b l I of t over m. So we need to just reflect this story here. So there is no x here, so this is 0. Minus b over m gets multiplied by x dot, and minus capital B times L times over M gets multiplied by I. Do you see a voltage in this equation? Therefore, it's going to stay 0. And according to this equation, di over dt is equal to minus r over li minus bl x dot over capital L plus 1 over L times V of A, which is input. Yes?
That'd be positive V over M.
For the second row, here? Yeah, because it's already on the right side. Yeah, thank you for the correction. So this has to be positive, which will make, if I can make it happen. So let me do this instead. Erase the negative sign. So this is positive BL over M for this. Thank you for the correction. So the I dot has no x in it. So again, this is 0. For x dot, we have minus BL over capital L. For I, we have minus R over L. And for V, we have 1 over L. So we have now both A and B matrices. And depending on what we want to do, the C matrix will be defined. So if the output of the system is position, this becomes 1, 0, 0 times x plus 0 times u. If the output of the system is velocity, 1 and 0 would switch places, so it becomes 0, 1, 0 plus 0 times. Okay, any questions? All right, so we've been developing models after models, the question is, what is the use of them? We've talked about um, a few applications, or without even solving a differential equation or solving to find the response of a system, you can tell how fast the system is. When we talked about the whole concept of time constant, you remember that from the model it was apparent that the time constant of a system was a certain value, therefore the speed of one system versus another one was either faster or slower. So the question is, what other information can we gather from just having the model? What else can we predict about the behavior of systems just based on their models, without, again, finding the actual response, without finding the actual solution to the differential equation or the transfer function or the state space model? The good news is we can get a lot of information out of just the models. And we can talk about how stable the systems are, how fast they are, what type of response would they present in when they have certain inputs or certain initial conditions in them. So that is going to be what we will be talking about going forward. Okay, so when we talk about time response, essentially we want to know if a known input is applied to the system, what would the output be? Let's just go back to the immediate example that we had. If we have a constant voltage applied to this speaker, how would the loudspeaker move? What is the displacement? What kind of displacement? How fast? Where would it find another equilibrium? Where would the equilibrium be? So if you look at this figure on the slide, this is a typical response of a second order system, and also sometimes a higher order system. So red shows you the input. So if you bring an input to the system at time 0, in response to that constant input, see this input is 0 before time 0 and comes on. It's like a switch that gives you a step. This is called a step input. And because the value of a step is 1, this is called a unit step input. So what you see here is unit step response. Because again, the input to the system is a unit step. So it's a step function. So what you see as blue is a typical response of a dynamic system to a step input. You can see that the system takes a little bit of time just realizing that there is a change in the input. So it's not immediately going to jump and follow the input. It would take a little bit of time, and that's how we know it's a dynamic system. It's not a static system. So this system takes a little bit of time and goes up in response, and maybe doesn't necessarily settle at where it's going to settle. It will, first of all, overshoot that final value, and then undershoot it, and then go over a few oscillations, and eventually settles. Now, there are a few important pieces that you need to recognize from this plot and keep in mind as we go forward. We already talked about steady state response. Steady state response is response after all changes have happened, and there is no longer any change over time. So you can see that the response of this system has settled at 1. So the steady state response of this system, therefore, is 1. It doesn't have to be 1, but in this case, the steady state response is equal to the input, which tells you that the DC gain, the gain of this system, is equal to 1. So the ratio of output over input, when it the system reaches a steady state, is 1. So that's another notion that we need to keep in mind. So it is called the DC gain of the system, which is the ratio of output over input in steady state. For this system, the DC gain is 1, because you give it an input of 1, it gives you an output of 1. So it's a 1-to-1 ratio. So we talked about the steady state, the DC gain. There is another time, if you start from the back and come backwards, there is this time that is indicated, and it's roughly for this system equal to 10-11 seconds. This is called the settling time. How long does it take for the system to reach a steady state? Now, it doesn't have to get on steady state itself. Normally and practically, you define a window and you say, as long as I get to a window, a 2% window of the steady state, I'm going to call that settling time. Now, how wide that window is or how small that window is our choice. But typically, that window is either 10%, 5%, 2%, 1%, depending on how accurate you want to be. So that as soon as the response reaches this window, you call this time the settling time. This is the overshoot. Normally, it's written in form of a percentage. What is the percentage of the first peak in response compared to the steady state response? That's called overshoot. This initial time that it takes for the response to go typically from 10% to 90% is called the rise time. So far we have talked about 4 or 5 characteristics of the response. So when you say, I want a system with rise time of this much, you indicate basically how quickly you want this response to basically react to changes in input. Or if I want the system to settle in 4 seconds. So you want all the changes in response to be done by 4 seconds. So these are numerical values that we can use to communicate what type of system we are trying to make or what type of system you're dealing with. Okay? And this is what is called a forced response. So there is an input involved. But there is another type of response where there is no input involved. You just give the system some initial conditions and you look at the response. And remember, we talked about the order of the system. Let me remind you again that the order of a system depending on what type of model you have, could be determined either from the highest time derivative, if you're talking about differential equation, or from the highest power of s, if you're talking about transfer function, or from the size of the state vector. How many elements are in the state vector that determines at the order of the system. Having talked about the order of the system, let's go ahead and revisit the first order models that we have developed. First order models that we have developed had this form. In differential equation, the standard form was the time constant, time derivative of the output plus the output is equal to another constant times u. Now we already know the significance of this constant. That's the time constant. That's an indication of the speed of the system. We didn't really talk about this constant, what is multiplied by u, but that constant is the DC gain. What was the DC gain? It was the ratio of output over input in steady state. And it should be relatively easy to see that this is the DC gain, because in steady state, what is equal to 0 in that differential equation? Let me zoom in so you can see better. In steady state, in this differential equation, what has to be equal to 0? Y dot has to be equal to 0. So the first portion of the differential equation basically vanishes. So what you have is y is equal to kdc times u. So the ratio of output over input, if you divide both sides by u, it's easy to see that that constant is that ratio. Okay? So what I said was, in steady states, let me write it down. So in steady state, we know y dot is 0. So that tells you that y is equal to k dc times u, which means k dc essentially is y divided by u, the ratio of output over input. So it tells you what the ratio of output over input is. Now, in the form of transfer function, again, when you bring your transfer function into the standard form, if you have a constant times s plus 1, this is going to be the time constant, the coefficient of s. But what is sitting in the numerator is your DC gain. What is sitting in the numerator is your DC gain. We'll talk about that, why that is the DC gain, when we further talk about the final value theorem. Final value theorem basically says, if you want to find the DC gain, set s equal to 0 in your transfer function. Set s equal to 0, in your transfer function, and it gives you the DC gain. If you set s equal to 0 in that transfer function, Ts disappears, so what is left is the constant in the numerator. So that was a quick review of what we can basically learn just simply by looking at the model. If you bring the model into a standard form, you already know the speed of response, and you already know where the response would settle if you give it a constant input based on the DC gain. So we already talked about finding the steady state response of the system. Simply you put the time differential, the dot term or the double dot terms equal to 0 in order to find the steady state response. So just as an example and a reminder, from this form of the differential equation, if you are after y steady state, if you want to know what y steady state is going to be, you can see that a times y steady state is equal to b times u. So for example, if u is equal to 1, if you give it a constant input of 1, y steady state is going to be y steady state is simply going to be b over a from that that form of the differential equation. If you take the other form of this differential equation, which is the standard form, y steady state becomes k dc times u, and under the exact same condition, you can see that y steady state is simply equal to DC gain, and that is the meaning of the DC gain. Just a quick short practice. Okay, so we talked about time constant and the significance of time constant and the fact that it shows how fast the system responds. And as a reminder, it's the time that it takes for a constant input, which is a step type response, to go from 0% to 63% of final value. That's the time that it takes. But if you, on the other hand, give it an initial condition, imagine a tank that is full, completely full, and at time 0, you open the valve at the bottom of the tank. The same time constant gives you the time that it takes for the system to change by 63%, which means changing by 63% meaning going from full to 37% of remaining in the tank. So that's the same. So if you want to plot the response, let me show you the plots. I think we did it, let's just do it one more time. So if this is time versus response of the system, if you have a unit step, the response looks like that. So it goes up and settles. If you have some initial conditions, so if you start off here instead of from 0, but no input, it basically takes the same trend and approaches 0 with the same speed. What I meant to do is a mirror image. So my point is, the speed of response doesn't really matter what kind of input you give it. It's the same speed because it comes from the dynamic of the system. It doesn't depend on what input or what initial condition you give it. It is going to be a consistent behavior no matter what the system receives. So if the input, for example, doubles, the steady state value of response doubles, but the speed of response remains the same. The time that it takes to get to 63% remains the same. So this is what is called a step response. And this is what is called an impulse response. And the reason we call this an impulse response is an impulse is a large input that happens over a very short period of time. Now keep that in mind and imagine a tank. An impulse response, if it is a reasonably small tank, an impulse response would be taking a bucket of water and dump it in the tank at time 0. How long does it take for the water to enter the tank? Very quick, but it's a significantly large amount of input. So a bucket being dumped in a tank is like an impulse response. So at time 0, the level of a tank immediately jumps, and then afterward it starts draining. So that's called an impulse response. A the step response would be if you open the valve at the top of the tank and give it a constant flow while the tank is empty. So the level gradually rises and reaches a steady state. Now this is just the tank, but you can have a similar type of step and impulse response for any system in it, including an electric system, so on. So for an electric system, for example, is that you just open the switch and close it quickly. So you get a quick surge in voltage, but you let the voltage drop down quickly. So that's an impulse type response. Or a step response is just to turn on the switch and let a constant voltage flow through the electric circuit. Okay, there are two definitions that are going to be quite important when we are dealing with transfer functions. The concept of pole and the concept of zero. These are both values of S. Now, values of S that make the denominator of a transfer function go to zero are poles of the system. It could be one pole if you're dealing with the first order system, or multiple poles if you're dealing with higher order systems. So if you look at this system, what is the pole of this system with the middle definition? What value of S will make the denominator go to zero? S equals negative A is the pole of the system. So let me write it down. So S equals minus L. A is the only pole of the system, and it has only one pole because it's a first order system. So one pole because it's first order system. That's the reason. Now, value or values of S that will make the numerator go to zero is called the zeros of the system. What value of S will make the numerator of this transfer function to go to zero? What value of S makes the numerator go to zero? Any? There is no. So that system does not have any zero. So the system has no zero. There is no value of S that would make the numerator go to zero. So there are no zeros involved here. So this is the typical response of a second order system. See if you have MATLAB on your computer. If you do, I can show you how to create this. If for any reason you don't have MATLAB, there is an online version of it that you can use, and that online version is at octave-online.net. So it's octave-online.net. So if you either it doesn't have MATLAB or you don't want to wait for MATLAB to come up, you can go to this website, and it's almost a complete version of MATLAB. So octave-online.net. So you can type your commands here at the bottom. You also can save your models if you register on this website, so it keeps your models. But if you're ready to follow along, let me show you what you can do to get to the step response of a system. So let's take another look. So let's say we have a system that has a DC gain of 5, which means if you give it a unit step input, the steady state response is going to be 5 times as large. The system has a time constant of 10 seconds. So it takes 10 seconds to get to 63%. Let's say the input is going to be, value of the input, the constant input is going to be 2, and you want to get to the response of this system. You want to actually plot the response of this system using MATLAB. Okay, so the steps are here. Let me go back. So you need to define your DC gain, the constants first. So your K underscore DC is 5. So I simply type KDC is equal to 5. If you put a semicolon, you can keep continuing. You don't have to execute this command. TC, which is the time constant, how much is it? It's 10. So 10 is the time constant. U, which is the value of input, is 2. Again, at each step, I put a semicolon. And then you want to introduce your variable S. So S is transfer function variable with a single quotation. So you say S is the transfer function variable. And then you define your transfer function. So you call it G, and in the numerator you have K dC, divided by, in the denominator you have TC times S plus 1. That's your transfer function. And then if you hit enter, it says, okay, I understand that you want a transfer function that has DC gain of 5 and time constant of 10, and that's my understanding of your transfer function, correct? Or if you made a mistake, go ahead and correct. If you have any difficulties, let me know, and I can come to your station. Okay, now we have a transfer function. So MATLAB understands that from this point on, G is going to be representing your system. And let's say you want to create the step response of this system. So there is, MATLAB has a command called step. So you type step, open parentheses. And in your case, we already defined U to be 2. So you say U times G. U times G. Basically, you're saying my input is U and my system is G, the transfer function that I just introduced, and then you close the parentheses. Okay? And as whenever you're ready, hit enter. And that's the response of the system that you get. So, like any computer simulation, you need to verify if this is really meaningful to you. So we have a few expectations from this system. The first expectation is that our steady state response should be 10. Why? Why the steady state response of the system should be equal to 10? Let's go back here. So the transfer function, G of S, is KDC, which is 5, divided by 10S plus 1. That's the transfer function. Now the DC gain is 5, and U is 2 with KDC of 5. So that tells you that Y steady state over U is equal to KDC, which is 5. So if U is 2, Y steady state has to be equal to 10. So if U is 2, which is like what we are representing here, so with U of 2, Y steady state has to be equal to 10. So we need to look at the plot that we got and see if the Y steady state is 10. Is it 10? So that's a positive indication. Now, what is the time constant of the system? How many seconds? Look at the model. What is the time constant of the system? 10. So, and 63% of 10 is 6.3. Does it take about 10 seconds to get to 6.3? Does it? If it does, then that's another indication that this is the correct behavior. Okay. MATLAB has, I believe, also an impulse function. So let me see if we can get impulse. So impulse of G. So if you give the system a unit impulse input, an input of 1 in form of impulse, it gives it an immediate jump in response at time 0, which again gradually goes down and gets to 0 in steady state. Now, how can you, if you only had this plot, if you only had this plot, could you calculate the time constant of this system? It said time constant is the time by which 63% of the change has already happened. Now the change in here is going from 0.5 to 0. So if when the response gets to 37% of initial value, means 63% of change has already been done, that's what you call your time constant. Now, what is 37% of 5? If you call it 40%, is roughly 0.2. So at 0.2, which is roughly here, you have your time constant. And the time constant is 10 seconds. Can you see that? Of course, it's not 0.4, it's 37%, so your time constant is there. So my point is, sometimes you can go the other way around. If you see the behavior of the system without having its model, you can get some indications of what the model should look like. So if I give you this plot, can you come up with the model for this system? The only thing I need to tell you is that this system received an input of 2. You can immediately look here and tell me the DC gain must be 5. So you have the numerator of the transfer function. You can look at this and calculate the time constant. So you have tau. So you have the transfer function. Can you see that? So by having the response of the system only the response, you can back calculate. You can go back and find the model of the system. And by the way, this is a wide area by itself. It's called system identification. Now this is simple. You know this is a first order system, but you know people make their living trying to come up with models for difficult systems like what? Like stock market. If you had a model of stock market, if you could, at least for one stock, predict the model, the behavior of the system, you could come up with an equation that basically tells you what the dynamics of going up and down of the price of that stock is, depending on probably various inputs. You could basically predict future. You have a mathematical model. Of course, depending on your assumptions and your data, that model could be right or wrong, but that you get the point. You can look at behavior of systems and try to come up with models for those systems. Make sense? Okay, so you have a tool. I introduce you to a quick online tool that has many of the MATLAB functions in it. So if you don't have MATLAB on your computers, that's fine. You can simply go to this website. Just bookmark this website so you can go back to it anytime you want. Any questions? Okay, so we talked about the time constant for a first order system. We talked about the DC gain for a first order system. We didn't quite talk about settling time. And we said settling time is when we get very close to steady state response of a system. But we didn't say how close. So this table here tells you the relationship between settling time and the time constant of the system. So if you want to get to 10% of the steady state response, the time that gets you to 10% neighborhood is 2.3 times the time constant. So if the time constant of a system is 10 seconds, it takes about 23 seconds to get to 10%. Let's test that on our system. So if the time constant of the system is 10 seconds, it takes like 23 seconds to get to 10% vicinity of 10, which is what? What is 10% vicinity of 10? It's getting to what number? Roughly 9. 10% of 10 is 1. So if you get to a neighborhood of 1 of 10, it should take about 23 seconds, and it's roughly correct. Now the table further says if your goal is to get to 5% vicinity, which is 9.5 in our example, it's going to take you 3 times the time constant. So about 30 seconds. So in about 30 seconds, you get to 9.5. If you want to get to 2%, which is like what? 9.8. It's going to take you 4 times as time constant. So it takes 40 seconds. So this is 9.8. And if you want to get to 1% vicinity, it's going to take 4.6 times time constant. So it takes like 46 seconds to get to 9.99. So depending on how close you want to get to steady state, it obviously takes more time. Now these are general formulas. It's not only applied to this system, any system. So again, this is the relationship. And we didn't talk about the rise time, but also rise times is related to the time constant. Okay. So all of what we said was time domain behavior of systems. We can also talk about frequency response of the exact same system. So if you go to MATLAB again and type Bode of G, this is Bode plot of our system. Basically, the first plot shows you the ratio between magnitude of output over magnitude of input. But what kind of input are we talking about? This is, by the way, called frequency response. So what is Bode plot? Let's review it one more time. It is basically response of the system, but to what input? Constant, time varying. If time varying, what kind of time varying function is the input to the system? The input to the system, U is sine omega t. Sine omega t. So if you excite your system with sine omega t, how will the system respond? What would be the output of the system? The output of the system is going to be A sine omega t plus phi. Which means what? Which means anytime you have a linear system like what we have here, this is a first order linear system, and you excite it with sinusoidal input, the output is going to be sinusoidal, exact same frequency. The only change would be its amplitude is going to be different, and there would be a phase shift. Now, how much would the amplitude be different, and what is going to be the phase shift is shown with the Bode plot. Bode plot basically tells you that the answer to amplitude change and phase depends on frequency of excitation. It's not a constant number. If you are exciting the system at low frequency, 10 to a negative 3 is fairly low frequency. Don't you agree? 10 to negative 3 means what? Means it takes 1,000 seconds for one cycle to happen. That's the meaning of 10 to the power 3. Versus 10 to power 1, 10 to power negative 1, and 10 to power 0. So this is one radians per second as the frequency. So when we are dealing with low frequency, the ratio of output over input is what? You can tell. You can read it off the magnitude. This is the ratio of output over ratio of input in decibel, by the way. Decibel is what? Decibel is 20 times log. So you need to bring that into understanding. But this is the ratio of output over input. So it follows the input until it reaches a certain frequency. After that, it's going to diminish the response. So the magnitude of response gets small. That's the typical Bode plot of a first order system. The same way we have a typical step response and we have a typical impulse response for a first order system. And this is the phase shift. So at the beginning, there is no phase shift, but eventually you get to a 90-degree phase lag. So the output would be behind the input. Okay, so we talked about the information you can gather simply by looking and analyzing your models. We discussed this about the first order system. Next time we'll expand this to second order systems. Thank you. Sorry I went over time a little bit.